You know, I'm very attractive. You could say I'm magnetic, right? Starting off the lesson with a joke. What is magnetism? Magnetism is one of those natural forces that occur in nature, and it also attracts and repels, just like electric charges. They also attract and repel. It follows the same structure, but please don't confuse a magnet's attraction repulsion to a charge's attraction and repulsion. They're completely different. Okay? So let's get started. This unit, or this part of the unit, discusses basic magnetism, the magnetic field of an a current carrying conductor, or a current in general. Then we're going to talk about magnetic forces, namely the force on a current carrying conductor, so the motor effect in the DC motor. And we finish this up with electromagnetic induction. So what happens, or how do we generate electricity using magnetism? As a friendly reminder, this big table, this list of things is what is in the curriculum, what's in the syllabus, and you need to know these things. So use this as a checklist to make sure that you understand things correctly. Like for example, if you read this, state the direction of the magnetic field at a point is the direction of the force on the north pole of a magnet at that point, and you understand what it means, you're good to go. Okay? If not, you need to revise. So let's get started with basic magnetism, right? First things first, you're familiar with what magnetic forces are. You have two general poles when it comes to magnets. They have a north pole and a south pole. North and north repel, just like charges repel, so like poles repel. South and south repels, north and south attracts, right? However, there is no such thing as a magnet that has only a north or only a south. You'll notice how I've left these diagrams just open. Sometimes we draw like a broken or a squiggly line. This means that I haven't drawn the rest of the magnet. A magnet must have both north and south poles. If you break it, it actually breaks into two smaller magnets, each with a north and south pole. So keep that in mind. Is there anything similar to neutral charge, like in electric charge? Not really, but there are certain metals that are technically neutral per se, meaning they get attracted to both north and south, and these are iron and steel. We call them ferromagnetic materials or ferrous materials. The word ferro or ferrous comes from the word ferrite, which means iron, because steel is an alloy of iron, and iron is already naturally magnetic, right? Now, if you bring iron or steel near a pole, a north pole or a south pole, it becomes magnetized. This phenomenon is called induced magnetism. Induced magnetism. Meaning, if I bring a piece of iron next to a north pole, it becomes magnetized first. It doesn't attract first. It becomes magnetized first. So think of it as having lots of little north and south poles. So the north and north repel, north and south attract. So this piece of iron becomes a magnet, with this end being north and this end being south. Then it gets attracted. Same thing with steel. If you bring a magnet or a north pole near a piece of steel, the far end becomes north, the closer end becomes south, it becomes magnetized, and then it gets attracted. The difference between iron and steel is that iron is considered a soft magnetic material, which means it's easy to magnetize, but it's also easy to demagnetize. It does not stay magnetized forever. So move the iron away from the magnet, it loses its magnetism. However, steel remains permanently magnetized. So it stays magnetized when it's removed away from that, North Pole, which is why we call this soft iron and hard steel. Soft and hard have nothing to do with the, hardness of the surface. It has everything to do with, is it easy for it to maintain its magnetism, or is it hard to do so? Okay? So if I want to make a permanent magnet, we use steel. If I want to make a temporary magnet, we use iron. Next up, what's a magnetic field? Just like electric charges, they had an electric field. Magnetic or magnets or magnetic poles also have a magnetic field. It is a region where magnets experience a force. It is a region where magnets experience a force. And just like charges, we draw the field from one side to another. In this case, we draw the field from north to south. We draw the field lines coming out of the North Pole and into the South Pole of a bar magnet. Why did we choose this direction? Because this is the direction of the force on a North Pole in that field. If I get a compass, a compass's needle is actually a magnet, with this end being north and this end being south. North and north repel, north and south attract, so a compass will always point away from the North Pole and towards the south, because it shows you the direction of the force on a North Pole. That's the field. Now, just like charges as well, the space between the lines shows you the strength of the field. The larger the space between the lines, the weaker the field is. The closer the space between the lines, the stronger the field is, which is why magnets are strongest at their poles. Look at this. Look at this. Look at how close the lines are to each other. Okay? Now, if I have a North Pole held in front of a South Pole and they're kept like far away from each other, or maybe this is a horseshoe magnet that kind of looks like this. You know, like those Tom and Jerry cartoons with a North Pole and a South Pole. The field exists between the North and South. This is called a uniform field. Okay. Easy peasy. Now, how do we determine the direction of a magnetic field? Like if I ask you to draw a magnetic field, it's a very simple experiment. You get a sheet of paper, you put the magnet on it, and then you get a compass. Remember, I said a compass's needle is actually nothing more than a magnet, with its tip being the North Pole and the back end being the South Pole. And it's allowed to move freely, like that needle, this magnet is allowed to rotate freely. So if you take that compass and you place it next to the North Pole, it'll point in a certain direction. You mark a point on that paper. Then move it somewhere else, mark a point on that paper. Move it somewhere else, mark a point on that paper. Move it somewhere else, mark a point on the paper. Do this several times. If you draw a line joining these points, you will end up with the magnetic field line. We don't do this once. We do this several times all around the compass in order to draw the field. So if I ask you to describe how to draw the field, these are your four basic steps. These are your four basic steps. You put a compass on a piece of paper around the magnet, check the direction of the needle, mark a point where it's, pointing, essentially, and draw a line through all of these points. Like repeat that several times all around the magnet, and you end up drawing the field. Yeah. Magnets are not the only thing that produce a magnetic field. Electric currents can produce a magnetic field. There is a reason why both of these units are together in the same unit, essentially, like electricity and magnetism. Because the source of magnetism is actually electricity. But let's stick to this for a second. If you get a wire, a very simple copper wire, and you pass a current through it, usually by, connecting it to a supply, so the current flows through. Let's say this is the positive side of the supply, this is the negative side of the supply. A current goes through, and that produces a magnetic field around the wire. The magnetic field produced by a wire does not have a north or south pole. It's virtually useless to us, at least for now. But it does have a direction. It's a bunch of concentric circles. It's just a bunch of circles all around that wire. And it does rotate, though. Proof is, if you put a compass next to the wire, it changes direction, which means there is a field. So how do we draw the field of a wire? I really shouldn't be saying of a wire. It's not the wire that produces the field. It's the current inside that produces the field. Because if I switch off the current, There'll be no field. So it's not the wire that's producing the field. This could be made of copper for all I care, which is not a magnetic substance. So it's not the wire that's producing the field, it's actually the flow of charge, it's the current that's producing the field. Now, this field can have one of two directions. Because it's just a bunch of circles, it can either rotate anti-clockwise or it could rotate clockwise. If the current is flowing out of the piece of paper upwards, or look at me skipping this rule for a second, or if I draw this in 2D, like you're looking at the top of that wire, and the current is going out of the page, it will rotate what? Anti-clockwise. But if the current is going into the page, often done by reversing the direction of the current, it rotates clockwise. We have a rule for that, a very basic hand rule. Now, this entire unit has like three or four hand rules. It'll make you look weird in front of an examiner or invigilator that's watching you in the exam. But let's take a look at how we use these rules. Now, I have to actually reverse my hands because the camera kind of flips things over. But here's my right hand, all right? Here's my right hand. If the current, and I'll try to zoom into this and align it so that it's like above where my hand is going to be. Yes, yes, this is good. This is good. Okay. If I have this wire and I tell you the current is out of the page, everybody with your right hand, give me a thumbs up. This thumb is out of the page. So the direction that my hand rotates, look at my hand, look at my hand, look at the direction it's going. It's going anti-clockwise. It's going anti-clockwise. So using your right hand, give a thumbs up, point it out of the page, and it will rotate anti-clockwise. If I reverse this, bring this guy here, and I tell you the current's into the page, give me a thumbs down, because your page is going to be on the desk. Give me a thumbs down. Obviously, please like this, not dislike. Haha. Thumbs down. How will it rotate? Huh? I'm going to point at you because that's down. Look at this. Clockwise. So try this out with your right hand, okay? So this is called the right hand grip rule. Yeah, I should make myself smaller again. Zoop. Hopefully not too small. Okay. Very good. Now, logically, if I want to make this field stronger, I can increase the current or decrease the current. But right now, this field is almost useless. To make it more useful, as in to have it produce a north and a south pole, we take the wire and we coil it. So we get something like a pen or a rod, we get the wire and we coil it all around, and this changes the shape of the field. This changes the shape of the field. You end up having, I'm just going to draw 4 lines in the middle here. You end up having the field go out of one side of the coil and into the other. Exactly like what? A bar magnet. Exactly like a bar magnet. This time, however, by the way, we call this a solenoid, not just a coil. We call this a solenoid. And this time, we find out the direction of the magnetic field also using the right-hand rule. But this time, your fingers are the coil, and therefore the current in the coil. And your thumb is the north pole. Your thumb is the north pole. Take a look at this. See, this is your right hand, okay? What you're looking for, if I zoom in here, what you're looking for is what is the direction of the current in the coil. Specifically, I want you to look at the open end of the coil. Like, look at this. The current goes into this side, crawls up, and then coils down here. Which means right now it's going this way. The green is the current. It goes up, goes back, goes up, goes back, and so on. Hold your hand near the open end of the coil. And then I want you to grip with your fingers so that your fingers are pointing in the same direction. Your fingers are pointing in the same direction as the coil. You have 2 types of grips. Either you grip away from you, or you grip towards you. If you grip towards you, your fingernails show you the direction of the current. So if it's downwards, like gripping towards you, كده, then this should be the North Pole, which it's not. But if I grip it this way, it is the North Pole. Look, North Pole is over here. Now, sometimes we're lazy enough to say that, hey, the North Pole is often near the negative side of the supply, which is most of the time true. So if you feel like you're completely lost in an exam and you like, boom, forgot this rule, like your head just completely forgets the rule, look at where the negative side of the coil should be. That probably is your north. Okay? If you forget it. Hopefully you don't. Now, a coil's magnetic field strength can be increased or decreased in strength. You can increase the strength of the magnetic field by either increasing the current or the voltage, increasing the number of turns, so using more loops, or using an iron core, meaning get a piece of iron first and then coil the wire around it. How does that help the field get stronger? Because when the coil gets a magnetic field through it, it magnetizes the iron. So the iron also becomes a magnet. So the iron also produces a field. And now you have two fields, one from the coil and one from the iron core. We good? Good. Now, what do we use this coil or solenoid for? Besides the usual, oh, it's an electromagnet, I can switch it on and off and attract things. There are a couple of applications which you could keep in mind. One is called a relay, and the other is a loudspeaker, just like how speakers work. A relay is a very special electrical component that we don't often see very much, by the way. But a relay is an electrical component that connects two separate circuits. It allows one circuit, let's call this circuit 1, to control a second circuit, circuit 2. Here's how it works. Look at the circuit on the left. Right now, the switch is open. So there's no current flowing through here. The relay consists of two parts, a coil, which is the solenoid, and an iron switch, a springy or a spring iron switch. Spring iron or spring iron means if you move it with a force, sure, it bends, but if you let it go, it goes back to its original position. However, if you decide to close this switch, click, a current now flows through the circuit, circuit 1. So this coil turns on and becomes magnetized, and therefore it attracts the iron switch, closing circuit 2, which causes a current to flow in circuit 2, turning the second circuit on, or the second light bulb on. Okay? If I open that first switch again, the iron or the coil demagnetizes, so the iron switch opens up again, and this lamp turns off. So you can use it to allow one circuit to switch on another circuit, or a low voltage circuit to switch on or off a high voltage circuit. That's what we usually use it for. Next, how does a speaker work? Like, not just big speakers, like even these earphones in my ear. How do these work? They have a magnet inside, a fixed bar magnet inside, like, or a magnet that looks like this. Now, this magnet in the middle is connected to the cone of the speaker. You know, when you go to these very large weddings or parties and they have these giant loudspeakers, and these cones over here, they vibrate in and out like boop, 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 boop. Now, this is what produces the sound, by the way. This cone vibrates forward and backwards, which vibrates the air molecules and produces sound waves. What causes it to vibrate? You have a coil. Let's change colors here for a second. You have a coil that's wrapped around this magnet. When you pass an alternating current through it, which is your music signal, this causes the coil to magnetize, but because it's alternating, depending on the music that you're listening to, it starts to flip. the direction all the time because the current keeps increasing and decreasing and changing. So the magnetic field keeps changing and changing, and it causes the magnet to vibrate in and out. It keeps getting attracted, repelled, attracted, repelled, attracted, repelled. And while it's doing that, it's also vibrating what? The cone. It's also vibrating what? The cone. Boom, 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 boom. And that produces sound. Very good. Easy peasy. Let's solve a few questions. The magnetic field of a bar magnet can be represented by magnetic field lines. Which diagram shows two magnetic field lines drawn correctly? Remember, the field goes out of the North Pole and into the South. So, out of the North, into the South. A. Very good. Next. Which row gives the metal used to make the core of an electromagnet and one property of the electromagnet? So what do we use? An iron or steel? Remember, I'm using an electromagnet, a coil, a solenoid. So it has to be iron. So it's either A or B. And then, what's the property of that iron? Is it temporary or magnet or permanent? It's soft, right? So it's a temporary magnet. So B is the answer. Good. Next. 29. Why should it be iron? Because iron is a temporary magnet. Because imagine if it was steel. Like, it's a good question. Imagine if it was steel. Isn't the whole point of an electromagnet that I can control it? I can make it stronger or weaker, switch it on or off. If I use iron, and I switch it off, like I open my switch, the iron turns off. Like the iron demagnetizes and it switches off. But if I use steel, I close the switch, it magnetizes. I open the switch, it does not demagnetize. It stays permanently magnetic. And I don't want that for an electromagnet. Remember, we said that the core over here has to be what? Iron. Good question. Next. The diagram shows the magnetic field around a solenoid carrying an electric current. What happens to the strength of the magnetic field and the distance between the field lines when the current is increased? Now, okay. If I increase the current, the field should get what? Stronger. Which means it should be either C or D. Then, if the field gets stronger, the distance between the lines should decrease because you now have more lines. So the distance between the lines decreases. So your answer is what? C. Okay? Very good. Next. An unmagnetized piece of soft iron is placed close to a strong permanent magnet as shown. What is the induced polarity of the end X? Like, what is the pole on end X of the soft iron, and in which direction does the magnetic force act on the soft iron? Now, obviously, if the iron gets magnetized, this side becomes south, this side becomes north. So X is south, so it's either C or D. Then, is the force attractive or repulsive? It's always attractive. So the direction of the force on the soft iron is to the left because it gets attracted. So C. C, your answer is always C. Uh-huh. I remember somebody giving a statistic a very long time ago about how most answers, like in a multiple choice exam on average, would be C. I don't know why or where they got that statistic from. We should look it up. Next, let's talk about electromagnetic induction, as in how do we generate electricity using magnetism. This section, or this part of the chapter, is split into three distinct parts. What is induction? Like, how do we generate electricity? The first application, which is the AC generator, which has a coil that spins. And the third application, which is the transformer, which increases and decreases voltage by using two coils. Let's discuss the concept of induction. Induction is what? Induction of EMF in a conductor moving across a magnetic field. Bravo, MSR, you can read. What do I mean? The word induction has many meanings, but you can assume for now that it means to generate. So it's you generating an EMF or producing a voltage in a conductor that's cutting, sometimes we use the term cutting, that's cutting a magnetic field, which means if you get a wire, like in this example, you get a wire and you start moving it up and down between the poles of a magnet, every time that wire cuts, look at the language, cuts a different magnetic field line, think of my fingers as, the field, it generates electricity. If you're not moving, like you're stationary, not moving, nothing happens. Okay? Even if I'm on a magnetic field line, the idea is to keep changing or cutting through a different magnetic field. So moving the wire generates electricity. You don't have to move the wire though. The important thing is that some kind of cutting action occurs. So either the wire could move or the magnet could move. So if you get a magnet and you start moving it in and out of the coil, what does it do? The magnetic field cuts through the coil, which does what? Generates a current or induces an EMF in the coil or in the solenoid. So again, you don't have to move the wire. You could move the magnet, okay? The important thing is that they're moving towards or away from each other. Like there's some cutting action going on. Because some people move the wire and the magnet together. Bravo, that does nothing. If you move them in the same direction, that does nothing because nothing's getting cut. Now, how do I increase the value of the induced EMF, like the value of the voltage induced? You can either move the wire faster, that means you're giving it more kinetic energy, using a stronger magnet, or increasing the number of turns. Okay? So again, induce means generate. Induce means generating electricity. Now, we use the word induction a lot because the examiner really likes that term. But if you don't use it and you end up using the term generating electricity, that's fine. But if I ask you for the name of this phenomenon, you have to call it electromagnetic induction. It's one of the few terms that you have to memorize as is. Now, besides these three factors, there's one more factor that affects how much you generate, and that is the direction of motion, or at least the angle of cutting. So if you have a wire that you're moving up and down, we say that you're cutting the field at 90 degrees or you're moving perpendicular to the field. This is the best method of generating electricity. It gives you maximum current or voltage in this case. But if I start moving the wire left and right, parallel to the field, look at my hands. I'm not cutting anything. It's moving between my fingers and it's not cutting any fingers. This generates nothing, zero. So moving perpendicular to the field generates maximum voltage. Moving parallel to the field generates nothing. Which logically means if you move at an angle, you're going to generate maximum and you're not going to generate zero. You're going to generate something in the middle. And the more parallel you are, the less voltage you generate. Because look at this, you take more time to cut the same lines compared to before, compared to this. But if you move the wire, your direction of motion is more vertical or perpendicular, this generates what? This generates more voltage. This generates more voltage because you're more perpendicular. The distance between the field lines is now shorter that you're cutting. Okay. Now, what about the direction of that current? Remember, we're generating a current. So what about that direction? Because if you look here in that first diagram, I've drawn the direction of the current. Like we've moved the wire up, so the current goes this way. But what if you move the wire down? Logic assumes that the current should move in the opposite direction. So how do we get that? And why didn't I draw the direction of the current for the coil? Because it's pretty hard. We have a law, or two laws actually, called Lenz's law and Fleming's right hand rule. Okay, Fleming's right hand. I'll show you how to use it. But first, Lenz's law. You're never going to be asked to state the name of the law. Now, let me get my head out of the way. You're never going to be asked to state the name of the law, but you do need to remember the definition, which is the direction of the induced EMF opposes the change causing it. Meaning, if I have a magnet and I move the north pole of the magnet, look at this. The north pole of the magnet is moving towards the coil. It generates a current inside the coil so that this side of the coil becomes north and this side becomes south. Because when you generate a current in the coil now has a magnetic field and it will always try to oppose you, meaning resist you. But if you're moving away from the coil, like if you get that same magnet, that same north pole, and you try to move it away from the coil, it generates a current in the opposite direction. So maybe instead of the current flowing here, it'll be this way. The current will flow in the opposite direction, right? Why does it reverse? Because you're moving in reverse, which generates the poles in the opposite directions. Because if you're trying to move away, it'll try to attract you, not repel you. It'll try to attract you. I always like to think of Lenz's law as a toxic relationship, and you'll get what I mean now. If you try to move closer to the coil, it says, nah, I don't want you. Move away. Get away. What are you doing? And if you try to move away now, it goes like, no, 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 don't leave me. Come back, please. It's a very toxic relationship, right? It always opposes you, closer or farther, it doesn't matter. Okay, that's how to use Lenz's law in the coil. Now, how do we find the direction of the current in a single wire? Should you memorize? Yes, you should memorize this definition. We will see this in questions later on, okay? Like, which often ask you, describe what determines the direction of the induced EMF. The direction of the induced EMF opposes the change causing it, or opposes the motion of the magnet, in this case. Okay. But now, instead of the solenoid, let's talk about just a simple wire. How did I know that the current in this wire would move up the wire or into the page? Like, how do I know that? We used Fleming's right-hand rule. With your right hand, again, with your right hand, this index finger is your magnetic field. Like, let me zoom into the picture of the hand first. Your index finger, all right? It's very hard to do, and keep my hand available, is your what? Magnetic field. Your middle finger is the current, and your thumb is the force, or your direction of motion, if you're moving the wire up or down. Always hold them at 90 degrees to each other. I should make myself bigger again. And actually, I'll move myself to the right side because the other picture is on the left. Right? Look at this. Look at this. So, magnetic field, current, force. If you try to use this on, oh, by the way, they should always be at 90 degrees. That was, I was trying to say that. Should always be at 90 degrees. I'm not going to aim the way you think I am, huh? I'm not going to. I know you want me to. I won't. Huh? Okay. But here, if we zoom in, to this wire. I want you to try this whole thing. The direction of the North Pole to the South Pole is your magnetic field. And the direction of motion is your thumb. And then you aim it from north to south. Now, forgive me, I'm not going to reverse my hand, even though the camera is like reversing me itself. It's like flipping my image over. But it won't work until I do that, unless I do that. So here's my right hand. This is my actual right hand. I had my left hand up because of the reversal, so it could look the same way in the diagram. But now I have to use my own right hand. First, North Pole, north to south. It's pointing to the right, at least to my right. And then the current is into the page. Now, hold on for a second. Pause. I'll get back to the right-hand rule in a bit. In a paper, in any exam paper, you have 6 directions. You have up, down, left, and right. Your normal up, down, left, right. And then you have out of the page as a direction or into the page as a direction. I know we've already tried the into the page thing with the right-hand grip rule, but now you can try it here. Even if it's an isometric diagram, like this 3D diagram over here is what we call an isometric because it's got like an angle over here. So if you try the north to south, if you try it from north to south, look at this, huh? North to south. And then the current is into the page because it's going away from you, then you're moving the wire up. Or if you're moving the wire up, the current is what? Into the page. Because using the right hand rule, you are the one that moves the wire. So you have the magnetic field from north to south. You have the force that's upwards, or the motion that's upwards. So the current is what? Into the page. If I reverse the direction of motion, like if I push this down, look at the way I turn my hand. I twist it like this. I twist my wrist. Sure, my elbow goes up a bit, but never flip your entire hand because your magnetic field needs to be at the same direction. So magnetic field is from north to south, force is downwards. This middle finger is now aiming at me. I can bite it like, towards me. Okay? Very good. This is Fleming's right-hand rule. And I'll be honest with you, you're not going to use this very much. Like, not the right-hand rule. Because there's a very similar left-hand rule for the motor effect, okay? But we're not going to use it that much. We're not going to use the right hand much. Left hand is a lot more. Okay. First application, the generator. What is the AC generator? It's a device that converts kinetic energy to electrical energy. You generate electricity. You are the one that grabs the coil over here, sometimes by, I don't know, connecting it to a bike handle or something. Like maybe you have a handle over here, maybe you have a bike pedal over here, and you're the one who turns it. Maybe there's a turbine. It consists of a coil. Like look at this generator. Let's zoom in. It consists of a coil, which is this thing over here. It's just a wire that's pivoted in the center. There's actually a pivot over here that you don't see. Placed in between the poles of a magnet. When you turn your handle, the coil also turns and rotates. So these two ends of the wire, like the left side and the right hand side, these two ends, these both move up and down and they cut through the magnetic field. Thus, they generate electricity. Electromagnetic induction occurs. Now, if you look at the rest of the construction, the end of the coil of each coil is connected to what we call a slip ring. Like it's a full round slip ring. This first ring is connected to the right side of the coil. The other one is connected to the left side of the coil. And when the coil rotates, the rings also rotate. They all go round and round. But they're also in contact with, but not stuck to, what we call carbon brushes. Stuck to over here, what we call carbon brushes. I still haven't described what their function is, like this function is, but I want to focus more on the generating electricity bit. So when you turn the coil, it generates electricity. Why? Because when the coil spins, the ends of the wire of the coils cut through the field, inducing electricity. How do I increase the voltage that we generate? The magnitude of the EMF, EMF is voltage. You can spin it faster, you can use a stronger magnet, or you can increase the number of turns. All three things will increase the voltage that you generate. Now here's the thing though. What's the point of these two? Like the slip rings and the carbon brush. If I was to connect the wires of the coil directly outside to a light bulb, for example, that I want to light up, like if I was to connect them directly to the coil, when the coil spins, it would grab these wires and spin them as well, breaking them in the process. What happens here instead is that the slip rings can spin, they're made of copper, with the coil, and they touch the brush, but they can move while keeping the brush steady. It doesn't move. So the function of the slip ring and the carbon brushes is to what? To conduct electricity to the output circuit without breaking the wires. That's it. You don't need to explain anymore. Good. Finally, the voltage that we generate using a generator is alternating, or AC. Remember how we defined, or we said that there are two types of currents. We have DC and AC. Now, DC is from a supply or a battery. We don't need that. AC, or alternating current, comes from a generator. It's produced by a generator. Now, how does it work? Like, why is it AC? Go back up to the previous page. Remember this bit? The bit with the angle? If you move up and down, you generate maximum voltage. If you move left and right, you generate zero voltage. If you move at an angle, the voltage changes a bit. But what if I'm not moving up, down, left, or right? What if I'm doing all of them at the same time? What if I'm moving in a circle? What if I'm moving in a circle? Like if this wire is moving in a circle. If you're spinning around in a circle, some of the time, you're cutting the field at 90 degrees, so maximum voltage. So this is the coil at maximum voltage. Then sometimes you're at an angle. You get a little bit less voltage. Then you're horizontal, zero voltage, nothing. Then you go down with an angle. So you get some voltage, but because now you're going down, the direction gets flipped. You don't get a positive voltage, you get a negative. Negative simply means that the direction of the current is reversed. Then you're here, you're moving perpendicular, maximum voltage again. Then you're here at an angle, so you get a little bit less voltage. Then you're here moving parallel, which means zero voltage again. But then you're up to increasing, maximum, decreasing, zero, increasing, maximum, decreasing, zero. So when you plot a graph of how the voltage changes over time as you spin the coil, this is what you get. An alternating current. Going up and down, up and down, up and down, up and down. A very common question is, what is the position of the coil? What is the position of the coil at maximum or at zero? The position of the coil at maximum voltage is horizontal. Why? Because this is where the two ends of the coil, so the left end and the right end of the coil, are moving up and down. So they're cutting the field at 90 degrees. Okay? But when the coil is vertical, this is when the ends are moving left and right. They're moving parallel to the field, so they're not doing any kind of cutting. You get zero voltage. Okay? So memorize these. These are very common. It's a very common question asking you, what is the position of the coil at maximum voltage and minimum voltage? Okay? Very good. My tea is cold now. Oh well. Last bit in electromagnetic induction is called the transformer. What is a transformer? It is a component or a device that either increases or decreases it. Decreases what? The voltage. I call it EMF because it's just voltage without losing power. Now, how does it work? So people ask me to microwave my tea without the how dare you? Yeah, well, I finished it anyway. You can drink some cold tea, that's fine. So how does a transformer work? A transformer actually consists of three separate components connected together. You have what we call a primary coil. This is made of copper. It is wound around what we call a soft iron core, a rectangular core. And then you have a secondary coil, also made of copper, wound on the other side. So here's how it generally works. And you'll see how it increases and decreases. But for now, let's look at how it generally works. Step one, you connect the primary coil to an AC supply, like an AC voltage supply. It has to be AC. Must be AC. When the alternating current goes in and goes through the coil, what does a current through a coil produce? Well, what does it produce? Magnetic field. So this produces a magnetic field. But hold on, instead of the field leaving like this way, like we're used to, that doesn't happen. No, 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 no. Instead, the iron core is looped, so it traps the field inside. We need this to happen. I'll show you why. So when the magnetic field goes through the iron core, what does it cut then? It goes through who? The secondary coil. It cuts through what? The secondary coil. And when a magnetic field cuts through the secondary coil, it generates a voltage output. So voltage AC is output, not ANT, out. So to simplify, voltage AC into the primary coil produces a magnetic field, a changing magnetic field. It has to move around. The magnetic field moves through the iron core and cuts the secondary coil, which generates electricity in the secondary coil. Now, you might be wondering, why not use DC? Because the important thing is that this magnetic field needs to be changing, aka moving, for electromagnetic induction to occur. Because imagine this. Remember what we said earlier on over here? If I move a magnet into and out of a coil, doesn't that moving magnetic field generate a voltage in the coil? Same thing here. If I were to use a DC supply, not an AC supply in this scenario, the DC, the voltage, the static, not changing, not moving, not increasing, decreasing voltage, would produce a magnetic field. That's not changing either. So it would produce a field, but the field wouldn't be moving. So would that generate electricity in the second coil? Is it continuously like moving and cutting in and out of the coil? No. It's like getting a magnet and holding it stationary next to the secondary coil. It's not going to generate anything. Nothing's moving. So we need it to be AC, not DC. Okay? Now, since we're generating electricity in the second coil using, the coil and the magnetic field, the number of turns affects the voltage. If the number of turns of the secondary coil is more than the primary, this causes the voltage of the secondary coil to increase. We call this a step-up transformer. So we increase the voltage. But if the number of turns of the secondary coil is less than the primary, this causes the voltage to decrease. This is sometimes what I want to do, by the way. Causes the voltage to decrease. We call it a step-down transformer. Okay? When it steps up and steps down, It steps up and down according to, look at the top of my head, like right up here. See? Look at this, look at this. According to this rule. The ratio of the turns is the ratio of the voltage. So Vp over Vs equals Np over Ns. So if I were to double the number of turns, the voltage would also double. If I were to half the number of turns, the voltage would also half. But when we increase or decrease the voltage, it doesn't increase out of nowhere. Because remember, energy cannot be created or destroyed. It's only changed from one form to another. So when we increase the voltage, something has to decrease in its place, and that's the current. And when we decrease the voltage, something has to increase in its place, and that's the current. Why? Because of the power rule and the law of conservation of energy. In electricity, power is V times I. And if everything is, efficient, 100% efficient, the power that goes into a transformer should be equal to the power that goes out, which means the V times I into a transformer should be equal to the V times I out of the transformer. If I were to increase the voltage, the current has to decrease to keep the same value, to keep the power value the same. Okay? So remember that. This is only in a transformer. Voltage and current are inversely proportional only in a transformer. I just mentioned this rule, this IP VP, current primary, voltage primary, equals current secondary, voltage secondary. But where do we use this? Like step down, we use it a lot. I'm charging my phone, I have my PC on, I'm charging my iPad, whatever it is. Most devices step down the voltage. The main supply is 200 volts. My phone needs 5 volts. I'm not gonna like throw away 295 volts. So we step down. But when do we step up? We step up when we transmit electricity in electrical cables. Because these cables are very, 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 I'm not being very eloquent here, very long, extremely long, like hundreds of kilometers long. This means they have very high resistance. Now, you might say, what's the problem? So what if they are very long and have high resistance? Any current that passes through any wire warms up the wire. The higher the current or the resistance, the more it warms up. So the power lost as heat in any wire is equal to I squared times R. Remember how we mentioned last time that this is going to be relevant? The amount of power that you lose in a cable depends on current and resistance. I have no choice but to have large resistance because I have no choice but to have super long wires. We're not living next to a power station. That's not happening. We live hundreds of kilometers away. So the only other way to decrease power loss is to decrease the current. So how do we do that? Let's say you generate 22,000 volts in the power station. You put a step-up transformer, which increases the voltage to 130, 200, 300,000 volts. It doesn't matter. What does that do? Decreases the current a lot, which decreases the power lost as heat in the wire a lot. I mean, a lot. It's like a lot squared because there's I squared. So if you half the current, the power loss decreases by 4 times. Like it's a quarter. It's a lot. And then you transmit the electricity. Now, obviously, my house can't use 132,000 volts. So before the house, we have what? Step down transformers. Right before the house, we have step down transformers, which do what? Decrease the voltage again. Sure, it does increase the current, but you know what? It's right next to the house. Like this transformer is very near your home. So that's fine. So we're not going to lose a lot of power there. So again, if I ask you, hey, why or when do we step up or why do we step up the voltage when transmitting electricity? Because that decreases the current, which reduces the heat lost in the cables, which lowers the what? Reduces energy lost and lowers the cost. Because if you think about it, the slower the current is, the thinner a wire I can use. Because large currents need very thick wires to not heat up. Low currents means I can use a smaller A wire. Okay? Remember, power lost in a cable is P equals I squared R. Let's solve a few questions. A wire is moved down in a direction perpendicular to the magnetic field. Three changes are suggested. The speed of the movement of the wire is increased. The magnetic field strength is decreased. The direction is reversed. Which changes increase the EMF, as in increase the voltage? Obviously, decreasing the field, increasing the speed will work. Decreasing the field strength will not work. It'll decrease. And reversing the direction does nothing. It will neither increase or decrease. So the answer is 1, B. Very good. Question 31. A wire is moved across a magnetic field. This causes an induced current in the wire. The induced current interacts with the magnetic field to produce a force on the wire. In which direction is this force? Ooh, okay. Okay, we're gonna use the right hand. Wait, no. I don't know the directions. He just said you move the wire across the field and it uses a current which interacts with the field to produce a force on the wire. This interaction with the magnetic field to produce a force is the resisting force. Remember Lenz's law? The opposing force. So in which direction is this force? I don't know, but I know it's going to oppose, not the current, oppose the change causing it. Which means you. In which direction are you trying to move it? So is it in the direction of the current? No. Is it in the direction of the motion of the wire? No. Is it opposite to the current? The current's not the reason. It's trying to oppose who? You. It's opposite direction of motion of the wire. So if I'm moving the wire down, the magnetic field and the current will try to push me back up. If I'm moving the wire up, the magnetic field and the current will try to push it down. Remember, toxic relationship. So D is my answer. Next. A 100% efficient step-down transformer has a primary voltage, Vp, and a primary current, Ip. Remember, it's a step-down transformer. So the voltage will decrease and the current will increase. Which row compares the secondary voltage and the secondary current with Ip and Vp? So secondary voltage decreases, so C or D, and the current increases, so C. Next. Figure 6.1 shows two bar magnets. On figure 6.1, sketch the pattern and the direction of the magnetic field lines between the bar magnets. So let's just sketch. By the way, you can get away with just drawing like 4 lines or so. I like to draw one in the middle, one on top, one on the bottom, and then one between each. If you want to curve the ones at the edge a little bit, go ahead, but you don't have to. When you guys write jokes in chat, kida, and I laugh, I think of the people watching the recording and thinking I'm crazy because I'm just laughing. There was a joke. I'm gonna say what the joke is. It's fun to let people guess. Now, figure 6.2 shows the same bar magnets with a coil of wire between them, and a handle is being spun. It's like rotating. Name the parts labeled A. Okay. Uh, what are these called? Slip rings, right? Slip rings. Nice one. The coil of wire is rotated in the direction shown. Draw an arrow to show the direction of the current in the coil. Explain your answer. My answer is I'm using Fleming's right hand rule. I'm using Fleming's right hand rule. But let's zoom in. My advice is always try this on a single end. Like, don't try it on both ends. It's only these ends that work. So pick one and use the rule. Pick one and use the rule. So again, here's the North Pole from north to south. Which side is going up? I'll move here. Which side is going up? This is going up. This is the force because it's going clockwise. So in which direction is the current? Huh? Into the field. Middle finger is pointing at you guys, into the field. If you try it out here, it's from north to south, but I'm moving it down, like I'm moving the right side down. The current is towards me. I can bite my finger. This is out of the field. Pick any one of them or draw both. I don't care. I just have to erase the force because the answer involves a drawing and I can't just draw randomly on the diagram anymore. Explain your answer. What's my answer? Using Fleming's left-hand rule, the field is from north to south, and the left side of the coil is going up. I just mentioned one of the directions. Honestly, it doesn't really need you to discuss the field's direction. I'm just saying it just in case because sometimes this type of question is worth more marks and you have to describe the directions of the field and the direction of motion that produced the current. Sorry, my bad. Fleming's right-hand rule. My brain was thinking left side of the coil, so it like wrote left over here. Fleming's right-hand rule, absolutely. Yes. Stay focused. Also remember to hydrate. My voice literally changes when I drink some water. Explain how rotating the coil in figure 6.2 continuously causes the galvanometer meter needle to show an alternating current. Ooh. First, what's a galvanometer? What's a galvanometer? We haven't seen that one before. I want you to think of a galvanometer like a voltmeter or an ammeter, like or both. Like it's literally a voltmeter, but it shows you the direction of the current. Again, it's just like a voltmeter, but it shows you the direction of the current. Shows you the direction of the what? Of the current. So if it keeps deflecting back and forth, it means that the direction of the current keeps changing back and forth. Okay? Okay. Now, here's the thing. Here's the thing. How do we explain this? Well, let's see. I have 4 marks. So if the coil is spinning, it does what? It cuts through the magnetic field. This induces a voltage. Now, keep in mind, earlier, I used to just interchangeably say, induces a voltage, induces a current, induces a voltage, induces a current. That's fine. But the proper term is that it induces a voltage or an EMF. We don't generate a current, we generate a voltage, and the voltage is what pushes the current through the circuit. Keep that in mind. So as the coil spins or rotates, it cuts through the magnetic field, which induces a voltage in the coil. This voltage pushes a current or produces a current in the galvanometer. And since the direction of and since the coil is rotating, the direction of the current will also what? change every half cycle. Because he wants you to explain all of this. Explain how rotating the coil causes the galvanometer meter to show, or needle to show, an alternating current. So we have to explain induction first, and then we have to explain that changing the direction of the rotation, not rotation, since it's going up and down, every half cycle, it changes the direction of the current. So as the coil rotates, it cuts through the magnetic field, inducing an EMF in the coil. This produces a current in the galvanometer that reverses every half rotation of the coil. Instead of half rotation, you can say every 180 degrees, because that's also fine. Because every time it finishes 180 degrees, it basically flips. Very good. Nice descriptive question. Moving on. Now it's a transformer question. The electricity supplied to a town is transmitted using a high voltage cable. The transformer in the town has a soft iron core. Now, remember, the word soft doesn't mean it's like physically soft. It's just, easy to magnetize, easy to demagnetize. No, you know the drill. Explain the principle of operation of a simple iron cored transformer. So how does a transformer work? That's the question. Explain how a transformer works. So how does it work? AC voltage into the primary coil produces a changing magnetic field, which goes through the iron core. The magnetic field cuts the secondary coil, which induces an EMF in the secondary coil. It doesn't matter if the question is worth 3 marks or 4 marks. The answer will always be the same. I'll even split them up. AC voltage into the primary coil produces a changing magnetic field, which goes through the iron core and cuts the secondary coil, inducing an EMF in it, or in the secondary coil. If the question is worth, let's make this bigger. Looks too small. If the question is worth 3 marks, you use the same answer. If it's worth 4 marks, you use the same answer. Doesn't matter. The transformer steps the supply voltage down from 220,000 volts to 33,000 volts. There are 450 turns in the secondary coil. What is the number of turns of the primary? Okay. Number of turns on the primary. Let's go. NP over NN equals VP over VS, which means NP, which is the number of turns on the primary, over NS, 450, equals VP, which is 220,000, over 33,000. And you get NP. 220,000 over 33,000 times 450, which gives me 3,000. Which makes sense. This is a step-down transformer, so the primary has to be more than the secondary. The electrical power transferred to the transformer by the high voltage cable is 77 megawatts. Mega is a capital M. So times 10 to the power of 6 or times a million. Calculate the current in the primary coil. So we have the power. I have the power. And I have the voltage. I need the current. So P equals VI. So I equals P over V, which is 77 10 to the power of 6, over, what's V? 220,000. What if he said, I want the current in the secondary coil? I would use the 33,000. Okay. This gives me 350. 350. Very good. Wow. Next. Oh, I remember this one. This is one of the most evil. Shouldn't the number of turns be lower? Sorry, I'll answer a question. We're getting the primary, not the secondary. Huh? Focus. Should be more in the primary, less in the secondary. Now, this is one of the most evil questions ever created, and I'll show you why. The diagram shows an AC generator. The graph, sorry, shows the potential difference between points X and points Y plotted against time. A positive value of PD indicates that X is more positive than Y. Which diagram shows the position of the coil at point P on the graph? Now, what's this? What's point P? Point P is negative, right? It's a negative value, which means he said that a positive value shows that X is positive than Y. Negative means X is negative and V and Y is positive. This means that the current should be flowing from Y to X. That's what it means. So, which diagram shows the position of the coil at point P, meaning maximum voltage and the currents flowing from Y to X? Well, we can simplify this by immediately canceling out B and D because a vertical coil generates nothing. And then now, remember, this is north and this is south. So I'm using Fleming's right-hand rule. And I'm going to apply it to this coil, to both these sides. I'll show you how. First, north to south. Okay, north to south, aiming this way. And then if I'm moving this up because it's going clockwise, the current here is going to flow into the wire, and therefore the current's going to flow out of the wire. Basically, the current's flowing this way. You're like, okay, mister, why is it so evil? Because have any of you noticed the difference between A and C? Look. Look closer. Look a little bit closer. And look over here. Can you tell the difference? It's not the slip rings themselves. It's the it's the connection to the slip. No, 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 it's not about the dot. It's about which end is connected to which slip ring. Look at this. This is stupid. It's so stupid. The current in both coils will be the same, regardless. The current is going to flow this way and this way, this way and this way. It's the same coil. But I want the answer that lets the current flow from Y to X, meaning if I go along with the current, flow into the coil, go out of the slip ring into X. Oh, this one's flowing from X to Y. If I do the same thing here, the current flows into the first ring into Y, then from Y to X. And this is my answer. This is one of the most ridiculous questions ever made. Because, I'm sorry, most people are not going to see this clearly. Heck, I don't even see clearly with my glasses on. So, yeah. You know, when you were a kid and you used to play those games that ask you to find the difference between the pictures. I was like, okay, okay, let's move on. Let's move on. Let's just move on. Let's just move. Last thing for today. No. Last thing for today. We're just pushing through. Let's talk about the force on a current carrying conductor or the motor. Last bit. When I say motor, it's the exact opposite of what we studied in the generator effect, which is if the generator effect involved me moving the wire through a field to generate electricity, this time I'm going to pass a current through the wire and it will move. I will pass a current through the wire and it will move. Okay? So how does it work? Take a look at this. Let's zoom in somewhere. Yes, come here. Basically, here's positive and negative of the supply. When a current flows through the wire and a wire is in between the poles of a magnet, this creates a magnetic field. So now you have two magnetic fields, the magnetic field of the wire and the magnetic field of the magnet, and they both interact. Now, I'm not going to go into the details of that interaction, but know that when two magnetic fields overlap and interact, this applies a force. So this wire experiences a force and it just boop, jumps up on its own. It'll jump up on its own. If I reverse the direction of the current, it'll move down instead. Like imagine that this wire is being held up by a couple of strings or springs. This wire can either float up some more or like stretch the springs down. So the wire experiences a force because of the what? The current in the magnetic field. So the question is, okay, how do we know the direction of the force? Well, just like we had Fleming's right-hand rule in induction, this time we have Fleming's what? Left-hand rule. This we will use very often. This we will use very often. Like in the previous questions we solved, I insisted on finding questions with the right-hand rule. Fleming only made two rules, so don't worry. He's not gonna stop me. I'm sorry. He's kind of dead if you think about it, and he can't make any more rules anymore. Bro's gone now, so it's just two rules now for now. Imagine if he was alive. Anyway, let's see. This time, keep in mind, same fingers as before. This is the force. This is your magnetic field, and this is your current. So FMI. Okay. I have the magnetic field and the current this time. I need to find the force. So using left-hand rule, you'll aim from north to south. Oh, I should make myself bigger. Hold on. Mhm. The power of streaming compels me. Ah, I'm bigger now. It still doesn't help that I have to put my hand in front of the camera. First, north to south, this way. Right? So look, my hand is just like that. North to south, this way. And the current is out of the page. So look at this, it's out of the page because it's moving towards me. You can't see it. I can bite it, but again, I'll try to make you see it. It's very hard to do. Out of the page towards me. So what's the direction of the force? Up, upwards. So this time you use Fleming's left-hand rule. Okay? Remember it like this. Left hand is the motor, right hand is the generator. Left hand is the motor, right hand is the generator. With your right hand, you produce electricity. With your left hand, you take the electricity away. Ah. I'm trying to be poetic, but I don't think it worked. Now, you can also do this if I change the diagram a little bit. Sometimes we draw the magnetic field like this. Just a bunch of X's, or I just draw a rectangle and I say the magnetic field is into the page. This is actually, if I have to sketch this in 3D, this is as if I'm holding the north pole of a magnet on top of a sheet of paper and the south pole of the magnet behind the paper. So now the magnetic field is getting into the paper. That's why it looks like this, right? So now with my Left hand, what do I do? With my left hand, what do I do? I aim into the board, and the current is flowing this way. So it's right in front of me. The current is flowing from left to right. The field is into it. The current is this way. So the force is what? Upwards. So be careful. Read the question carefully. Look at the labels carefully. Question will always tell you everything you have. Okay. Now, obviously, I can increase the strength of the force. I can increase the strength of the force by increasing the current, or by using a stronger magnet, or by having more than one wire in the field. So we use this concept to build my final device, the DC motor. What is the DC motor? Deja vu, anyone? Doesn't this look like the generator? Just a little bit. Two differences. First, this has a battery or a supply. A generator does not. We generate electricity in a generator. Here, we don't want to generate. We want to give it electricity. We want to provide it with electricity. And then you also have what we call a split ring this time around, not a slip ring. Not you don't have two rings, you have one ring that's split. And the other end of the coil is often connected to something like a wheel in the case of a car, like an electric car, think Teslas and stuff. Or although Chinese like EVs are getting really good now. Or maybe it's a fan, an electric fan that's spinning, right? Or your food processor that you use to cut up some vegetables and like regardless. When a current flows from the battery into the carbon brush, into the split ring, and into the coil, this creates what? A current in the coil, which produces a force on the two ends of the coil using Fleming's left-hand rule, north to south. One of them has the current going into, so that side goes down, the right side goes down. And then the other has the current out of, so it goes up, the force goes up, and it ends up rotating clockwise. That's the motor. It's literally just like the generator. That's the motor. You can make it spin faster by, what do you guys think? Let me make myself smaller again because I don't need to take up that much space anymore. Hmm. I can increase the speed of the motor by increasing the voltage or the current. More turns. So instead of one loop, you get 10 loops, 15 loops, 20 loops. The more loops, the better. Or using a stronger magnet. This time, however, this split ring, and forgive me for this typo, this is supposed to be split ring. The function of the split ring does what? It reverses the direction of the current every 180 degrees to keep the coil rotating in the same direction. Because without it, the coil would not move, it would stall, it would stop like this. Now, I'm going to briefly explain it, but it's not necessary, honestly, because in an exam, we always just mention this statement and that's it. If, uh, if this is your coil, if the right hand goes up and the left hand goes down, like, or here I am, right hand goes up, left side goes down. It rotates this way. The moment the right side goes up and it reaches the top, the right side of the coil now needs to go down. And the only way to do that is to reverse the current. The split ring does it for me. The split ring does it for me. That's all you need to know. The split ring reverses the current every 180 degrees. Now, anybody who's kind of observant will notice that if this is the 2D cross section of the brush and the rings, at a certain point, that empty gap in that split ring is going to be not touching anything. Like it's going to be in between the brushes. So how does the coil keep spinning? Because it already has momentum or kinetic energy. So it uses its own kinetic energy to keep spinning just so that they can eventually touch the other side as they spin. Okay? So even that is solved on its own. Like it does everything on its own. I don't need to do anything myself. Now, final thing, and I promise. Sometimes a magnetic field doesn't affect a coil. And it's not a magnet that affects the coil. It's a wire affecting another wire. Look at this. If you have two wires next to each other, and they both have a current, they're both copper wire. This is wire A. If a current is flowing up through A, doesn't this create that, remember that useless field we talked about? It's not going to be very useless anymore. When this field cuts through the second wire, and the second wire also has a current through it, can't I use Fleming's left-hand rule? Huh? This is the direction. I'll change my colors frequently here. Sorry about that. This is the direction of the magnetic field. And the current's direction is up the wire. So that's the current. So magnetic field, and the current is up. Okay, sorry. Magnetic field, and the current is up. So it experiences a what? I'm trying to do this. A force this way. So the wire experiences a force to the left. How is this the direction of the magnetic field? Because the magnetic field goes around in a circle, right? It goes around in a circle. So I just looked at the direction of the field at that moment as a tangent to that circle over here. It's going this way. Use your right-hand grip rule. Huh? Current's up, going anti-clockwise. It's fine. But here's the thing. Wire B also has a magnetic field. So when wire B creates a field, it passes through wire A, which creates a force on wire A. So the field of A applies a force on B, and the field of B applies a force on A. And the forces are always in opposite directions. Now, a small thing to have you memorize, and it never changes. If the currents are in the same direction, like they're both going up or down the wire together, these two forces, if you try the left-hand rule twice on each wire, they will always be attractive. So if the currents are in the same direction, they just attract. But if you try this out and you reverse just one of them, not both, you reverse just one of them, both forces change direction, so they both repel. If you want a quick explanation to describe, you can say the magnetic field of A applies a force on B. The magnetic field of B applies a force on A, and they're equal in value, opposite in direction. Yeah. Let's solve a couple of questions and finish this. This one is an easy one, and you'll see this again in atomic physics, whether it's an alpha particle or a beta particle or a gamma ray, it's the same thing. Now, before I even solve this question, remember, using Fleming's left-hand rule, okay? But the current, which is my middle finger, is the direction of what? The current of positive charges, not of negative charges, of positive charges. Keep that in mind. An electron moves into a uniform magnetic field. The arrow shows the initial direction of motion of the electron. The direction of the magnetic field is into the page. What's the direction of, does a force act on the electron when it enters the field? Okay. Magnetic field is into the page, so I'm aiming at the board, or at the screen, or at the paper. And the electron is moving this way, right? So it's moving in this direction. So the force should be upwards. Nah. Force will be down. Why? Because this middle finger is the direction of the flow of a positive charge. This middle finger is the direction of the flow of a positive charge. But an electron is a negative charge. So you either just reverse the force or you twist your hand so that the current flows opposite to the direction of the electron. I don't bother with that, by the way. I just say, oh yeah, it's an electron, it's the opposite force. Proton goes up, alpha particles go up, electrons go down, beta particles go down. So towards the bottom of the page. Okay, next. Figure 8.1 shows a horizontal flat coil in a magnetic field. The coil is connected to a cell. The coil rotates. Determine the direction of movement of the side AB relative to the plane of the coil. So will AB go up or down? Now you might be confused, but you need to be observant, remember? Huh? Be very observant. Zoom in some more, zoom in some more. Ah, look at this. Here's the positive, here's the negative. So the current flows this way, boom, into the side. I don't care about the other side. I just want AB. Ah, Fleming's what? Left-hand rule, north to south, into, the force is what? Upwards. Sorry, my bad. North to south. Okay, okay, I should make myself bigger so you can all see. There we go. North to south. Uh-huh. And the current is into, so the force is a downwards, not upwards. Downwards. So it goes down. Okay. Next up. Explain how you determined the direction. So how did I figure out that direction? Uh, I mean, I used what? I used Fleming's left-hand rule. But that's not how you describe it. Remember, you have to mention the directions of the current and the direction of the magnetic field, and therefore the forces in which direction. So you'll say, using Fleming's left-hand rule, the magnetic field is from north to south, and the current. Oh, I'm sorry. Thank you. I'm too big for the screen. Oh, I'm so big. I'm too big for the screen. Am I big enough now? Sorry. I'll keep my ego in check. Okay. 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 Using Fleming's left-hand rule, the magnetic field is from north to south, and the current is from A to B. So the force is downwards. And try to add this bit, perpendicular to the field. For some reason, the examiner really likes mentioning that all of these things are perpendicular to each other when we're describing how we got that force. Okay, good. Very nice. Wait, I have a big concern, by the way. I have a big concern. This is supposed to be a motor, right? But it doesn't have a split ring. So what's going to happen to it when it does reach that vertical position? It's going to what? It's going to stall or keep shaking because it doesn't know where to go. Like it can't go down anymore. It can't go down this way. So it stays stuck in a vertical position, right? So it stops in this vertical position or it stalls. And that's what the next question is. State and explain what happens to the coil as it reaches the vertical position. It stops and it stops turning. Why? Because at that moment, the forces have not been reversed. The forces have not been reversed. So there's no moment anymore. Like the forces are up and down. They're parallel to the coil. There's no more force. Sorry, there's no more moment. Okay. So what's my statement? The coil will stall or stop in the vertical position as the forces have not then reverse. So the moment will be zero. There will be no moment. Because when you have forces on the left and the right side, that creates moments, making a turn. Next. To operate as a motor, a split ring commutator, that's the full name for a split ring, by the way, like the full legal name, split ring commutator, and brushes are added to the parts shown. Explain the effects of the split ring commutator and the brushes. Oh, he wants the full effect, like the full description, right? So what do they do? The split ring and brushes do the following. Reverse the direction of the current every 180 degrees to keep the coil rotating in the same direction. But that's 3 marks, right? It's 3 marks. So I'm just going to add without breaking the wires. Because that's the function of the brushes. Like, that's still one function. Because without it, the wires would break. If this could spin, it would still break the connection to the battery. But that's why we need both the brushes and the split ring. Reverses the direction of the current every 180 degrees or half cycle to keep the coil rotating in the same direction without breaking the wires. Very good. Next. Final questions. My final set. I think that's the end of it. Yeah. Last two. The diagram shows a wire hanging freely between the poles of a magnet. There's a current shown. Okay? The magnet and the current cause a force to act on the wire. What is the direction of this force? Keep in mind, you have 6 directions, left, right, up and down, and in and out. If 4 of those directions are taken, because north to south is left and right, the current is up and down, you only have the in and out left. You only have the in and out left. You can never have, so it's technically 3 axes, horizontal, vertical, and in and out. The vertical is taken by the current, the horizontal is taken by the magnetic field, so the force has to be in or out. Yeah, Fleming's left-hand rule. I'm not going to change my size anymore. I'm big enough for the paper, right? So north to south. Wait, is that it? Yeah, north to south. I'll zoom in. Okay, not that much. Come on. Why'd you do that? Okay, north to south. And the current is down. Look at this. It's down the wire. So my thumb is into the page. My thumb is what? Into the page. It's pointing at you guys. So the force is into the page, away from me. Okay? In and out food so good made its way into physics. Yes, absolutely. I've never had in and out before though. I make my own food. I make really good food. Which component forms part of a DC motor? You can say, I can cook. Which component forms part of a DC motor but not a simple AC generator? So what's in a motor but not in an AC generator? A coil, that's in both. That's in both. Brushes, that's in both. The magnet, that's in both. The split ring, that's only in the motor, not the generator. So D is my answer. Ta-na-na-na. And ladies and gentlemen, we are now done with magnetism.